My name is Saborno Isaac Berry from Berry Science Lab, and today we're going to be talking about potential. Welcome back to electromagnetism. Now, what is potential? Well, you probably remember gravitational potential as U equals mgh. How is that connected to force, which is minus mg? Well, some of you probably know that force is actually defined as the negative derivative of potential with respect to position. But that's only for the 1D case. So what happens with the 2D or beyond case? Well, then we start having to define force as a vector instead of a scalar. And to go along with that, potential is still going to have to be a scalar, unfortunately. So what do we do in this case? Well, we use something that turns a scalar into a vector and still takes derivatives. And that is in the form of the gradient. See, the gradient of a scalar u is equal to the partial derivative in one direction, comma, the partial derivative in another direction, comma, the partial derivative in another direction, and so on and so forth. So that's the gradient of potential in classical mechanics. But now we're dealing with electrostatics. And so in electrostatics, we're dealing with a potential that looks like this, even though it has mostly the same properties. The electric force is actually going to be equal to minus dV dx. Actually, the electric field. So what are the properties of this potential? This is going to be minus gradient. What are the properties of this potential? Well, first of all, consider the electrostatic charge. Just a static particle, right? So we know that this guy is going to emit an electric field equivalent to 1 over 4 pi epsilon naught r squared
Positive, right?
q r hat. So this is the electric field according to Coulomb's law of this charge with magnitude q. Now, let me ask you for a second, what is r hat? Well, it's the unit radial vector, of course, which is just going to be x, y, z divided by r. And r cubed is just going to be what? X squared plus y squared plus z squared to the 3 halves. I know that's unreadable. That's the point. So, what happens when we try to calculate the curl of this? Well, let's see. What is the curl? Well, as you might expect, it works quite like the cross product of two vectors. We covered this in the first lecture. So let's try calculating the curl by hand. What's the curl formula, first of all, because I keep forgetting it. Let's see, ijk, partial x, partial y, partial z. Ex, ey, ez. So you're going to get partial y ez minus partial z ey, partial zex minus partial xez, partial xey minus partial yex. So now let's see what happens when we plug in. You get all of these components are either x over x squared plus y squared plus z squared to the 3 halves, or y or z. So what does this look like? Well, everything's going to be symmetrical. Just to get an idea, let's calculate the first component. Partial y of y over x squared plus z squared plus y squared. to the 3 halves. Here it looks like we're going to have to use the product rule. So you take 1 over the behemoth. And then here we have to differentiate x squared plus z squared plus y squared to the minus 3 halves, which essentially works like c plus y squared. And to take the derivative of that, we just use the chain rule and the power rule by taking this fella out, raising this to the minus 5 halves, and then taking the y squared derivative out by writing this as minus 3y. So this becomes minus 3y squared divided by the same thing to the 5 halves. All right, and what happens? Well, first, let's actually take the common denominator. Probably a smart idea. So this becomes x squared plus z squared minus 2y squared over x squared plus y squared plus z squared to the 5 halves. And of course, since z is just all of this, but with swapped elements, these two are going to cancel out, these two are going to cancel out, these two are going to cancel out. The curl of the electric field for a static charge is going to disappear. Now, this only holds for static charges. When we start getting into electrodynamics, things are going to start getting a lot more complicated. So, now let's talk about potential. This feature is incredibly useful for potential, but what are some other properties of potential? Well, as you might have guessed, potential in a gravitational field needs to have a point of reference from which you measure height. You need to measure height from, say, y equals 0, which can be the bottom of a cliff, sometimes it can be the top of a cliff, sometimes it can be the rest length of a spring. Who knows what it is? But whatever it is, you need a reference point where you place the origin. The same way, you need a reference point for the electric potential. But just in the same way that whatever reference point you use only affects the potential, but doesn't affect the actual system, whatever reference point you use only affects the potential here as well. Why? Well, once you take a derivative, what happens if you set, let's say you have a potential at H1, and under these conditions, okay, so let's say we have potential 1, and under these conditions, our guy is at H1. Then potential with reference point 2 has our guy at H2, which means that the potential here is NGH1, the potential here is NGH2. The only thing that changes is a constant. In fact, you can now write NGH1 plus x of t, NGH2 plus x of t. And so when you subtract these from one another, all you have in the end is NGH1 minus H2. This H1, this H2, they're all constants that immediately go away as soon as you're smacked with the derivative or the gradient. And so it doesn't matter what reference point you choose as long as we can agree on it. So the reference point you typically see used is negative infinity or positive infinity. Taking the potential at infinity is the most popular way to calculate potentials. But you have to realize that sometimes, for example, with a uniform infinite plane of potential, which spreads its potential everywhere, which spreads the electric field everywhere, even the potential at infinity will actually blow up and give you an infinity when you take the integral. Yeah, a case in point. Because of this definition, you can actually write potential as the path integral of E over some curve. So, you usually take it to infinity, either positive or negative, but sometimes that's a very bad decision. So you have to be careful when you want to evaluate the potential, and always try to make it explicit if you're not using infinity if you want to evaluate this potential. So that's what electric potential is and some of its properties. Thank you everyone for watching.